Hey there, I'm Sneha Chandra at Exun, and I welcome you to the Exun Talks. Aurojit Panda is an assistant professor in computer science at New York University. His main interests are distributed systems and networking. He got a PhD in computer science from UC Berkeley in 2017. He has worked on operating system kernels at Microsoft and on network functions at Nepali. He has received UC Berkeley's Dmitry Angelikos Memorial Achievement Award in 2017, a VMware Early Career Faculty Award in 2018, a Google Research Scholar Award in 2021, and an NSF Career Award in 2021. A long time ago, he spent 6 years at DPS Archipuram and as a part of Exum Clan. Thank you so much, sir, for joining us today. I'll hand over the platform to you now.
Thanks. Great. So thanks for having me. I'm going to be talking about algorithms for the internet, and in particular, sorry, just give me a second. The main goal here is I want to tell you a bit about BGP, which is this routing algorithm that's connecting the internet, and talk about why its correctness isn't so much dependent on technical stuff or about algorithms, but rather about assumptions about how people behave and how companies behave. And then I'm going to talk a bit about how some changes in how the internet is being used today versus how it was, how this algorithm, how it was when this algorithm was designed in the 90s, has been leading to some problems, but how exploring how addressing these problems and finding fixes to them has become harder, in part because of how the world has changed since the 90s. So let's start with BGP and routing. So, actually, before that, let me just answer this first question about why. So, the reason I wanted to talk about this is twofold. First, I'm I grew up in the 90s and the 2000s. I left India in 2002, and so to me, the internet has always been like a cornerstone of what has led me to where I am. And I think the internet has had a pretty profound impact on humanity. And we tend to take it for granted. We think of other things as providing maybe there's some concerns about certain internet services, but we generally think the internet itself is going to be there forever. And part of this talk is to convince you that's not the case. Now, the problem is if it needs to change, someone needs to change it. And I work with a bunch of people, we are academics who keep talking about how the internet should change, but we can't make these changes. No one cares. Like we are just yelling into the, into the void. Companies who are the other players are not incentivized to do so. Like if you're a company, you want to maximize profits, you don't want to improve the internet necessarily. So really to get this done, we need like more active participation from uh, people, the people who use the internet, pressure on the government or what the policies should be. That's what matters. And this is why I think it's useful to understand this topic. And in terms of why me, it's partly because this is what I work on, and this is one of the things I work on, and because my advisor Scott has like spent most of his life on this, and it's good to talk about things people like. Okay, so let me talk about routing. So basically, the way to think about routing is the following: you can think of any network, including the internet, as a big graph. And the graph has a few things. It has computers. So for example, in this case, it has laptops belonging to me and my friend Kay, and a whole bunch of other servers, for example, ones belonging to Zoom or Google or SteamYard. And then there are a bunch of more passive network devices like switches or routers and a bunch of edges, links, that are connecting things together. And routing essentially asks the question, how does data from my laptop get to, say, SteamYard, where we're watching this right now? And one way to do this is for some algorithm to go look at the graph and compute exactly what happens at each step and what links should be taken to produce a path. You can think of this as very similar to mapping out a path when you're looking at a map of, say, Delhi or of India. Now, the problem is that this works well if you have a map, if you have a global internet map, but we don't. We really don't ever have a notion of a global map. So instead, what we need to do is do something that is a bit more distributed. And so the way we do it is We have people individually announce things, such as like SteamYard might announce something like I am SteamYard, and the switch that is attached to it takes this announcement and says, hey, I can reach SteamYard, uh, and it's at a distance of 1 away from me. And then switches next to it say, hey, I can reach SteamYard, I'm a distance of 2 away from it, and so on and so forth. And the idea with these announcements is that each intermediate step of the node in the path has a notion of what is the small, about whether they can reach StreamYard and what is the length. Now, the thing to notice here is that every single node has multiple paths through to StreamYard. So the question is, of these paths, which ones should it choose? Okay, the primary goal here is we don't want to have cycles, and by cycles I mean we don't want to have something like my machine sends data to the first switch, which then sends data to the second switch, which then sends it back to the first switch. That would be very bad because it would essentially mean we're never finishing what I want. And we also want to produce routes when possible. So the way we do this is that there's an observation that shortest paths are by definition have no loops. And the way to think about this is if you had a path that went A, B, A, C, then you could safely drop the BA loop, the BA part, and go AC and get a shorter path that does exactly the same thing. So shortest paths have no loops. And if you're in an environment where everyone is announcing all of their paths, then shortest paths is what gives you no loops. And this is like a pretty fundamental part of how routing works. Okay. Now, the problem is this doesn't work on the internet. So shortest path routing has never been what the internet has been based on. And the reason for this has been that links, which are the edges of this graph, and switches and routers, which are the vertices of this graph, the nodes, they cost money and they're owned by different organizations. So for example, some of these might be owned by Tata, and some of these might be owned by Reliance, and some of these might be owned by, like AT&T or Verizon. And each of them wants to maximize their profit. Like these things require repair. They have to roll out trucks every now and then to replace them. Someone needs to pay for this shit. So given that someone needs to pay for this, you want to do this thing of you only want everyone only wants to carry traffic that is profitable to them. So for example, in this case, you might have a pink node who has this nice relation with blue where blue pays them money. So we would nominally say that blue is a customer of pink's, in which case the pink node will tell blue that, hey, I can reach Zoom. This is how much it costs. This is how long the path is to me. But on the other hand, to the yellow node, who again, it isn't paying it, it might say, no, I cannot reach Zoom. Please don't try to send traffic through me. If you do, I'm not going to forward this traffic. The other part is if you are a node that receives two different paths, you want to take the cheapest path and not the shortest one. So in this case, if you look carefully, or again can read my rather horrible handwriting, the blue node has two possible paths to SteamYard. One is a long path that goes through yellow and orange, and the other is a short path that goes directly to SteamYard. Now, in both cases, it can reach SteamYard, but the problem is that the path that goes through yellow is very cheap. It costs, let's say, $2 per Gbps, while the shorter path is more expensive and costs $5 for whatever reason. So in this case, the blue path is incentivized to pick the longer path. And this is important, right? So remember, we started with this premise that shortest paths have no loops. The entire point of routing is we want to avoid loops. But now we have this nice thing that because of monetary concerns, we have to give up on shortest paths, and we might potentially use longer paths. And this brings back the original concern. What if there are cycles? How do we make sure, what if there is disconnection on the internet? How do we make sure that everyone on the internet can talk to each other? And how do we make sure that when you send traffic on the internet, it's actually delivered? So this was a question that became very important in the mid 90s when essentially the internet started being commercialized. So pre mid 90s, most of the internet infrastructure was owned by governments. So in India, this was EarNet. In the United States, this was NSFNet. In the UK, there was a similar organization, and it was only in 93 or 94 when people said when actually it started with a series of countries passing regulations saying that the internet should be developed for commercial exploitation, that this started becoming a question. Okay, so how do you fix this? Okay, so the first one is how can we fix cycles? The one way to do that is to basically is to say that okay, distance is no longer enough. Rather than sending distances, let's increase the complexity of our messages. Let's increase the size of them and send the path out. The idea being that you can now observe the path and decide if your decision is going to create a cycle or not. So you can say, hey, if I see A, B, then this is not the right path because there's a cycle here. And if not, you're fine. And the assumption here, of course, is that correct routers don't create loops. Okay, so maybe cycles are solved. The problem is this isn't sufficient by itself. So the reason it isn't sufficient by itself is that not only do we want routes that are without cycles, we also want routes that are stable. And what I mean by stable is that we want routes that continue to operate for a long amount of time. The reason is that every time routes on the internet change from one path to another, some amount of traffic has to be dropped. It leads to user perceptible uh, degradation. So if you are running Microsoft or Google or Meta's Knox, anytime you see rapid path changes, you basically start making calls asking people to fix their goddamn network and not have route flaps. Okay, now, everything that I said is set up to induce route flaps. So in particular, consider this particular example. So this is called a BGP gadget, and it's a very common thing that we teach students when they take undergraduate networking. But this gadget basically works the following way. We have four different networks, A, B, C, and D, and we're only going to consider how everyone reaches D. And because of the pricing mechanism, we end up in this place where A's cheapest path is ACD. Its next cheapest path is the next more expensive path is AD, and the next more expensive path is ACBD. So A will always want to go ACD, then AD, then ACBD. Similarly, B's cheapest path is BAD, then BD, and so on, and C has a similar thing. So what happens in this case is that you might start out in a place where, in the leftmost figure, where the paths are set up so that traffic from B goes BAD, traffic from A goes AD, and traffic from C goes CD. However, at this point, A notices that, hey, C has a path available. It's cheaper for me. I should switch over. And so what A will do is A will go from ACD. B will notice this change. It'll see that A's path has changed and will start going BD. And we've suddenly changed the path that we're taking. Now, again, we might have C will notice this, start going CBD, and again, we'll be back to a configuration where routes have changed again. Now, from this third configuration, B will again notice that a cheaper path is available and switch over. So we end up in this world where routes keep switching, and this is really bad for performance. The other problem is that there is no mechanism here that prevents someone from making a bad announcement. And what I mean by that is, consider this router over here next to Zoom. This router has no path to SteamYard that is of length 1. So there is no reasonable path to SteamYard. But nothing in the mechanism that I've talked about so far prevents it from just injecting a false announcement where it says, hey, I can reach SteamYard and I can do it for cheap. Okay, so these problems have existed since the 90s. As I said, this is not a new problem. And we actually thought that these were not real problems until well into the mid 2000s. And the reason is because of economic assumptions. So there's a couple of people, Lixin Gao and Jen Rexford. Jen Rexford is currently, or like Lixin Gao, I think, is at UCLA. Jen Rexford is at Princeton, who showed that the route stability issue that I presented is actually an example of arbitrage. So arbitrage is the standard economic concept of if it's cheaper for me, if the cost of some item is different, or the cost of an item is different in different places, I can basically buy in one place, sell in the other, and make a tidy profit because even though in reality the economic costs should not allow me to do that. Now, the thing with route stability is if you assume that the only reason people want to route traffic is because they want to earn money for their links, then they shouldn't be committing arbitrage. Economically rational agents, and what I mean by economically rational agents are basically networks and users who are self-interested and whose self-interest is entirely dictated by delivering traffic and getting paid for traffic, have absolutely no incentive to do this. So in practice, we would expect no route stability issues on the internet. Similarly, correct announcements are rational. So, put simply, I am unlikely to pay my internet provider, which in this case happens to be Verizon, for receiving traffic intended for my friend K. After all, if the traffic was intended for my friend K, why the hell am I paying for it? It costs me money. Now, the problem is that this is kind of a strange assumption because rationality itself, as I said, depends on the agent's utility. So I started with this assumption that what agents want, or what networks want, or what users want is to receive traffic intended for them and to get paid for delivering traffic. The problem is that these incentives are not true any longer. You often will get more money by having traffic intended for someone else or by taking paths that are suboptimal. So why might that be? So, to reiterate where we are, right? So we've been saying that we should carry only traffic that is profitable, and you'll only get paid if you deliver the traffic. But here's the thing. If I impersonate an e-commerce site or a bank or an anti-spam service, getting other people's passwords or getting other people's money transfers or getting other people's credit card information does in fact allow me to gain profit. In fact, the profits from this might far exceed the profits from actually delivering traffic to the right place. Similarly, if I am in some country where I need to censor a website, for example, YouTube or Facebook or or Twitter or whatever, or TikTok, the easiest way to do that is to have the government or have some external entity pretend to be to be that company. So, as you might know, TikTok in India is censored. One way India could have done this, though I do not believe it does it this way, is to start a server and say, hey, this is the TikTok server, and announce that to everyone in India and say, look, you can reach here for free. ISPs are incentivized to send traffic to that server, and all that server would end up saying is, yeah, TikTok is banned, please don't come here. But it's not just wrong destinations that are profitable, even long routes are profitable. So metadata collection, which has become an increasingly common part of how, like private companies and governments make their money, is essentially requires having traffic flow through links they control. Long, like if I can sell metadata that is worth and enough metadata to preserve to pay off my link, I'm actually incentivized to have you send your data through, even if it costs, even if it's actually more expensive for me to maintain the link. Okay, now these all might sound like hypothetical problems. It might sound like I'm Chicken Little yelling that the world is falling down, but these problems have been going on for a while. So earlier this year, in August 2022, Amazon was attacked. The attackers impersonated servers belonging to a cryptocurrency exchange called Seller. Uh, it took I believe, about like an hour or 45 minutes for Amazon to actually fix this problem. But during the time, $235,000 worth of cryptocurrencies were lost. Um, means this seems fairly small, but we know of cases where people have managed to steal a lot more. Similarly, in 2013, Spam House, which is a provider of spam protection services, went offline. And basically, what happened was a whole bunch of spammers banded together and said, we've had enough with with the spam protection website, and they essentially impersonated a Spam House server. They used BGP to inject paths that sent all of Spam House's traffic to them, and basically reported that everything was not spam. Again, this is a case where the spammers actually found that they were making more money by defeating Spam House than they were actually paying for doing this. Okay, so if we look at the problem, the real issue here is that we don't have identity and we have a lack of information. So in particular, remember the problem here is that anyone can pretend to be Amazon, and anyone can pretend add and anyone can lie about a path. For example, I can have you take a path that goes through me and say, actually, no, I'm not present in this path. I'm just going to omit this information. So what we need is a way to ensure that that the destination that lies at the end of the path is in fact correct. So Amazon is in fact Amazon. We also need a way to check that the network path actually is the path that you're taking. Okay, so this leads to this classic conundrum that this cartoon from the New Yorker captured in the early 2000s, which is on the internet, we don't know how to do identity. Nobody knows if you're a dog. So okay, things are actually not that bad. We have some mechanisms we can do. So in particular, since the 80s, we have this nice hammer we call digital signatures. And what digital signatures allow you to do is they allow you to authenticate a statement. And the basic idea is you can think of it as a function that takes a key, which is assumed to be secret, and takes a statement of fact, and it produces an output. Anyone can check that the output was in fact produced by the right key, does in fact contain the statement that's being asserted, but no one else can produce this signature as long as the key is retained or as long as the key is not available widely. So what this allows is for SteamYard to say something like, hey, I'm going to produce a signed statement saying I'm SteamYard. And for anyone to announce that they have a path to SteamYard, they must include the signed statement and also a signed statement from all of the intermediate nodes showing that this is the path that they took to get to SteamYard. So this is roughly an idea that has been floating around on the internet for about, I'd say, like 10 or 15 years, and there are at least 4 different guises of this. There's BGPsec, RPKI, and Scion, and various other versions that basically build on this core infrastructure. Okay, the problem is, let's say I want to send traffic to StreamYard. Okay, it means I had never heard of this website until earlier today. How the hell do I know who StreamYard is? How do I know what the key is? How do I actually figure out that the path is correct? So the problem really is something like this, right? So suppose someone who looks very different from me comes up and says, hey, I am Aurojit Panda. How do you know that they are in fact who they say they are? Or how do you know that I am in fact Aurojit Panda? And in some sense, similar to the internet, you are assuming that no one has incentivized to give this talk. Or you're depending on the fact that there are some people in the audience who have met me in the past, and they can say that, yeah, he looks and sounds sort of like what we remember, right? So what is this person, or what is this entity that binds a key to an actual identity? Who's to say that this key is indeed StreamYard's key? So the standard answer to this in the academic world is called the PKI assumption, or the public key infrastructure assumption. And the way to look at what the PKI assumption says is it says that there is a magical oracle in the sky that can correctly associate a key with any entity. Now, the problem is that any PKI authority has the ability to disconnect or attack anyone. So to see it's very simple. If the PKI administrator wants to disconnect SteamYard, they can just replace SteamYard's key with a key that they control. SteamYard can no longer sign statements that say that this is a path to SteamYard or I am SteamYard because, well, why should I believe that you're SteamYard? The PKI says that your key doesn't match SteamYard's key. Similarly, in terms of attack, once they have replaced this key, they can go start a server that does the same thing. Okay, so this leads to a very real world question. Who the hell runs a PKI? So the traditional answer used to be that, maybe ICANN should do it. ICANN is the internet assigned naming authority. The problem with ICANN is that and INA and similar organizations is they are entities created and owned by the US government. So countries such as China or Russia or even like very legitimate countries like the UK or Australia, which are parts of various American uh, allegiances, are not willing to trust a US government company to run this. Okay, so nation states are a problem. People have talked about having the UN run this, but given the UN status and how it works, this is a problem. People have talked about commercial entities running this. The problem with commercial entities running these things is that commercial entities really are controlled by the country in which they're registered. So again, we run into the same problem as nation states. So the entire question comes down to who runs this. Now, people have been working on this problem for a really long time, and we've seen all sorts of things like decomposing and making this hierarchical. So the hierarchical idea becomes that yes, there is a single PKI entity that controls the master key, but then they can delegate authority to smaller groups that are more locally trusted. But again, even in the hierarchy, the root of the hierarchy always has too much power. And that's generally the issue. Okay. So the problem that has finally happened then is that, even though these mechanisms have been known for about 20 years, only about 6 to 15% of networks have these policies deployed. So a few friends of mine, including Yossi Gilad, who's now at the Hebrew University, and Michael Shapira, tried to look at what happens at low deployment rates. And what they essentially found is that it's completely useless. It uses up resources, it takes time, but it doesn't help anything. And so this is really the problem, right? We know the technical solution to these problems. However, we can't deploy these because the thing that gates deploying these solutions is agreement and cooperation. It's policies, it's economics. And no amount of algorithms, cleverness will fix this. So, if you are watching at home, maybe you're thinking that, oh, the blockchain fixes this. Yeah, everyone thinks the blockchain fixes everything. I have written papers saying that blockchain will fix this at some point. No, it doesn't. Like, really, this is a social issue. This has nothing to do with technology. And that gets me to my summary. So, like many years ago when I was in Exun, was in school, I used to think of the structure of what I was supposed to do as specialize. And what I mean by specialize is that really it was that, hey, I am interested in computers, I'm interested in programming, I'm interested in being this geeky person who works on this. I should basically know how to program really well, and other things don't matter. And when I was growing up, like things like machine learning or social networks are things that are more obviously, even the news now talks about how these things are affecting society, were not things. But in reality, what I hope this talk convinces you is this is not the first time algorithms have had to interface with politics, laws, or other things. And while, social networks and machine learning might be affecting politics and laws, this is a case where politics and laws affect what we are doing, right? So they affect how the internet works and how other things work. And I think this is what it took me a long time to recognize, right? So maintaining these large pieces of technical infrastructure, building good computer systems, building good networks, building good things is not a technical problem. A lot of it is actually a policy problem. There are lots and lots of problems that we can solve today, except for the part where we don't know policy. And this means that, when you're thinking about computer science or when you're thinking about these programming problems, don't think about them in isolation. You really do need to be aware of the world around you. You do really need to be aware of the politics around you. And things which have been happening in, for example, the last 5 or 10 years, when the world has increasingly started fracturing, and we've also seen a lot more divisive policies in politics, they're actually a much bigger threat to how our technical landscape looks than really any of the technical problems, including like the end of Moore's law or other things that are facing us. That's all I have. It was great talking to all of you. Thanks.
Thank you so much for joining us, sir. And thank
Thanks.
you, everybody who attended this
Thank you.
talk. If you want more information about Exun Talks, check out exun.co/talks. Thank you.
Thanks.